Hi everyone, welcome to this episode of PhD presentations made for ISRM Deep Mining Commission. My name is Ashkan Rastegarmanesh. I'm going to be presenting today about the topic of my PhD, which was axial behavior of cable bolts under various loading and bonding conditions, which I completed at University of Southern Queensland on 2022. A brief background about me is that I have my bachelor's and master's in mining engineering, and I have a PhD in rock mechanics from University of Southern Queensland, which was mostly focused on cable bolts. And my industry background is some mining engineering work and mostly tunnel and shaft engineering works. These are some of the outputs of my PhD program and the publications that we made. Feel free to check any of them. And obviously the thesis itself, which is the bulk of the information, is available online on the university website. You just have to either search the title of this presentation or my name, and it will come up and you can see the details of the things that I'm presenting today there. The outline of the presentation is going to be a few slides on introductions of cable bolts, and then we talk about some literature work. We are not going to be that deep inside of it. We just want to get some information, and then we mention the objectives that we had for these PhD programs, and larger scale and smaller scale tests, and numerical modeling. We had some very small studies on barrel and wedge and rotations, which I'm going to mention briefly at the end. And in the end, we are going to have the conclusions and recommendations. Considering this is a presentation of the PhD, I prefer to focus on the things that are important during the PhD time. And by that, I mean the process rather than the outcome. And I hope that by the end of this presentation, people who want to follow this path or they want to continue this research, whether they are researchers or PhD students or people in the industry, they have a catalog of information that they can look onto. Rather than getting into the details of the tests and the graphs and behaviors, I try to mostly focus on pictures and some of the processes that we went through that led to the results that we had. And I hope that you guys enjoy it. And you can always go back to the thesis and the papers for the details and all the other small details that you guys might be interested in. So what are cable bolts? So the name cable bolts are basically in mining, they mean a type of the support structure that's made of, it's very similar to a rope. It's like a normal rope made of fabric or plastic, but here is made of steel, made of metal. And sometimes it calls wire ropes, but we call it cables for sake of brevity here. So cable bolts are basically made of strands. So strands are individual parts of the cable that are wound together and they make a cable bolt. So that's a terminology that I'm going to use here. I put two pictures here from in 1996 and 2000s, and you wouldn't be surprised if you study other works of cable bolts to see that there is different nomenclatures for different parts of the cable. As you can see in this picture, for example, this strand, the author of this study used the term strand for the whole cable. But again, for my study going forward, I'm going to use a strand, the term strand for what here is called a wire, and then the cable is this whole unit together. And inside the cable, we can either have a plain cable or a bolt cable. So a plain cable is a cable that's basically plain. It's like a simple, there is nothing on it. A bolt cable is a combination of all of these things that you see here. So again, a different terminology. Bird cage, nut cage, mini cage, or any kinds of other word, which basically are these enlarged structures inside the cables. We just call them bolts. And a cable that has that, we call it a bolt cable. So again, that's another simplification that I use. So plain cables are basically opposite of board cables. And on the cables itself, some of them, sometimes the strands are like smooth, so there is nothing on them, it's like a piece of metal, or they have indentations. So indentations are like patterns that have been printed on them. And so basically when I mentioned the term smooth, is the opposite of indented cable. And we see the pictures of them down the line. So the first question that many people ask is that what's the difference between cable bolts and rock bolts? And why do we have two of them? So cables are flexible. By flexible, I mean that they're physically flexible. So they bend, so they have lower bending moments. That means that you can put a large amount of them on a drum and deliver them inside the underground space and apply them. One of the limitations of rock bolts is that rock bolt length is always limited by the size of the opening that you want to support. And eventually, if you want to put a 4-meter rock bolt in a 2x2 or 3x3 space, it's basically impossible. But cables can be stored in a drum, so they can be like basically wound around the drum and delivered and be used there. So cables can be longer. Cable making process is different from rock bolt building process. Again, we are not going to go to the details of it, but rock bolts generally are made by quenching. So they are very hot, they put them in liquid, that's how they build them. But cables are made by cold drying, which is a different process. For sake of conversation, cables can go up to 1800 MPa, more or less. But usually rock bolts are around like 400, 500, even less than that, MPa uniaxial tensile strength. Even though cables and rock bolts on paper have higher surface area, nominal surface area, because they don't have all of those small voids and bits and pieces. But at the end of the day, because the building process is different, cable bolts are usually able to carry more stress. So, and cables can be modified by 100 different ways. They are like very, even though like rock bolts nowadays are very modifiable, you can customize them. But cable bolts, you can put bulbs on them, you can change the indentation of the surface, you can have like different conditions of them, you can have double of them, twin cables, 3 of them, you can put multiple of them in one hole. So there is a lot of diversity that goes there. All in all, that means that cables are very popular in high stress areas because sometimes you need much longer cables that go deeper into the ground, and some challenging ground conditions where you have lots of movement or lots of unusual and unconventional stresses and movements and changes in the ground condition. So cables tend to be more suited for those areas. When we want to study the cable bolts, there are different ways that we can break it down. Here I use this terminology. You are free to follow it or not, but this is something that I used for my PhD. So I use the term tendons as overarching terms for rock bolts and cable bolts. Here we are studying cable bolts. We can study them in shear and axial. So when we study cables in shear, we are basically guillotining the cable where the movement of our blocks are basically perpendicular to the axis of cable. Where in axial, the movement of the cable is basically parallel to the movement of our block. So we are basically pulling the cable out. In shear, we can do single shear and double shear, and in axial, we can do single embedment and double embedment. And the difference between them, I will briefly mention down the line in the next few slides. There have been many studies on cable bolts over the years. Some of them studied them in a single embedment test, which basically very similar. So very simple. We had the embedment section, which the cable was grouted or resin inside, and the cable was pulled out. And you see some of the works that over time has been done, and different types of the tests, and the typical graphs that you get from them, where you have a initial load pickup, and then you have a post-peak oscillations or behavior that we have in the corner. Some other tests that are some of the examples of the people who have worked in this area. You see, for example, you see tests that had you were able to fix the radial stiffness and pressure during the test around your embedment length, or the test where you stop the rotation of the sample, Or here on the corner right, you, for example, see double embedment test, where you have two embedded sections, and you are trying to force the cable to fail in one of those sections. And the main reasons that we had them was because of the termination method, which hopefully I mentioned that down the line. Looking at the analytical and pull-out behavior of the cable, basically what we mostly accepted is that if you look at on the right, when you start to pull out a cable or a rock bolt in this case, what happens is that you are not mobilizing the whole length of embedment at one go. So if you have a 10-meter cable in the ground, and you're pulling out from one side, you're probably only using a fraction of the length of the cable. And that's this length of the pickup that you see. This is sometimes called a zipper effect in industry when they are designing the capacity of the cables and rock bolts. Over time, as we increase the length, what happens is that you have a point of peak axial stress. And after that point, which is sometimes it's called a neutral point, as you can see here, towards the collar, you start to have diminishing stress, and your load pickup section on the left, or in this section on the right, it keeps moving to the right, to the left, and this debonding plane starts to move towards the end of inside your embedment column and towards the end. And eventually you get to a point that you have full debonding, so you have no capacity. And this is something that has been already seen inside the instrumented rock bolts and cable bolts during pull-out. So this is something that we more or less accepted, that you have a pickup length, you have a neutral point, and you have anchoring length, and over the length of the test, this keeps developing. So objective of my research program, my PhD, was to obviously have tests that give us the load and displacement curve, because that's given. We wanted to test larger scale and smaller scale tests. Larger scale tests are very expensive, very time consuming, difficult to do. Smaller scale tests, we wanted to have an alternative and test that. We wanted to test grout on resin, so chemical resin and cementitious grout. We wanted to see the effect of the barrel and wedge, because one of the reasons we have single embedment and double embedment over years is that to terminate the cables, you can either use a barrel and wedge, which is the assembly to stop the cable. This is what you use in the industry. Or you can remove that because of some complications and put another longer section of the embedment length that basically forces the failure to happen in the other smaller section. We wanted to study the effect of rotation, which is something that, a convoluted topic that in other studies have been mentioned. And we wanted to study as a continuation of rotation, we wanted to see the effect of the entry and exit point. So entry point is where the fresh cable is going inside the column, and the exit point is where the cable is coming out when you're pulling it out. We wanted to see the effect of the monotonic and cyclic testing. Cyclic testing here for us was mostly what happens over the length of the design length of the cable, and basically see if any deteriorations happens or if the load loss happens during when the cable is installed underground, during the different stress changes and different displacements. And we wanted to see the condition of the annulus, we wanted to see the condition of the external confinement, and eventually wanted to have some numerical modeling. So the larger scale testing that we did, this is the final version of it, which had few features or few things going for it. So we used concrete instead of rock because it was easier to cast and procure on site for us. We use a split pipe confinement. So around our external confinement of our concrete was basically a big pipe that we cut in half, and we put flanges on it. And on those flanges we put bolts, and we used the preload torque on those bolts as one of the variables of our test. We sort of use a double confinement test, even though we use a barrel and wedge. So we had the anti-rotation plate, which was a plate that here you can see went on top of our sample, confined the end top of the sample, and inside of it, inside this hollow ram jack, there was an anchor tube that would slide inside of it and stop the rotation and move the rotation to these wings that were connected to the external confinement. So everything was moving vertically up and down together. And I already mentioned the preload on the bolts and the barrel and wedge for reaction on the top, so that's there. Or here in this picture, you see the barrel and wedge. And we had rifled anchor tubes to make sure anchor tubes are not debonded. And we had core-filled cables, so we filled the inside of our cables. So those are some of the things that we had going for our test. Some of the pictures of the preliminary testing and different versions of our apparatus before it became finalized. So on the left section on the top, you see the first version of our test where we didn't have concrete, we just wanted to test everything. So that was our loading plate, our load cell, our hollow ram, and we had our LVDT and the reaction plate on the top. This test didn't work because our threaded section failed. So instead of using this, we basically went for barrel and wedge. But here you see the anti-rotation plate, you see the anchor tubes with the rifling inside of them, and the welded section on them, which was like sliding through this section. We had a loading plate with different sizes on the top to study the effect of the confinement on the top of the borehole when we are pulling out the cable, and different versions of it. And this was the anti-rotation plate that we end up with, which is a much more robust way of doing it. And this is a picture of, on the right, we see the picture of our external confinement. The cables that we used throughout this study, we used 6 cables. All of them were provided by Genmar, which is a very big, one of the biggest providers of cables and rock bolts in Australia. We had, so here in this table, basically we see the details of them, the diameter of them, and the breaking point load at the strand and barrel and wedge. So we had 2 smaller cables, which are these 2 cables on here, or these 2 cables, that we see here. One of them, so these 2 had around 22 millimeter diameter, and one of them was a plain cable, the other one had indentation of it, so it was a indented super strand. So the name of them were super strand, that's a commercial name. So IDS or SS, that's how we refer to them. The other cable was a 100-ton cable, which is a plain cable, which was the highest capacity cable at the time, which is a very big cable here, the Gulayev cable, or we call it GUL. That's a code that we use them. And we had 3 cables that they had bulb in them. So 9S-strand cable, 10S-strand cable, and 12S-strand cables. And these are the details of them which we see here. The commercial name of them was Sumo cables. And we see them here. And this was the cables when we prepared them. So we had a foam on the bottom section of this. The reason was that we wanted to have 300 millimeter embedment throughout the test. So we added another 150 in the bottom. So when we pull out 100, 120, we still have fresh cable inside our column of the embedment. So we don't lose embedment over time as we are pulling out our cable. And some other small bits and pieces that were necessary for a test. For our concrete samples, we had column formworks, which were 300 mm in diameter. We cut them 450 length, and we had these PVC pipes, which were our boreholes. The diameter of them was based on the manufacturer recommended diameter of annulus for each cable. And we put cables around, like wires around them, to have sort of rifling. And we do that to make sure that our failure only happens on a cable grout or resin interface, not between the grout or resin and rock interface. And this is the pouring of the grout and pouring of the resin on the right and left. Our resin was a 2-part resin, which was exothermic. You mix them together. It's around up to around I think 100 degrees Celsius, and then it mixes together in a few seconds. It hardens, and after some small time, it's going to be fully ready. And there's some testing that we did on the samples. This is the load disbursement curves that we got for them, or stress strain curve for cementitious grout, which was a stratobinder, a product of Minova, and our resin, which was a product of Minova, which for Carbofix. Again, Minova is another very big producer of this type of material, and the loads that we get on them. What's notable is that our resin type of the failure is more like a strain hardening with a much lower loads compared to our cementitious grout, which had a behavior very similar to cement or concrete. This is a final picture of the test, how it was and different parts of it. The output from the test, we had 2 LVDTs for displacement and 1 load cell for load. This green line was a load cell over time, the value that we would get. Typically, we had a load pickup, and then we get to a peak value, and then we had oscillations. Each of these oscillations were accompanied with a very loud noise, and like a jump of the sample. This orange line is the stroke like how much vertical displacement, how much pull-out happened. And this small line here, the blue line, is basically the movement of the LVDT at the barrel language. After the test, we open up the samples. You can see the inside of the samples. So that's the external confinement. That's the infill grout, the concrete, which was our main confinement, our grout, our cable, that foam that I mentioned, and those holes for the bolts that we put there. And this is the same on the right. We see the same for the resin. The type of the graphs we get from our samples, I'm not going to go through each of them. The details of them are in the thesis, and the explanation of all of these graphs are inside the papers. So please feel free to go and see them. But this is just a type of the output we get from them. Our hashtag basically means that we let rotation happen, and when we don't have a hashtag, that means that rotation was constrained during the test. And for different cables, we see the different values that we get. For our bolt cables, we see lots of oscillations. For our smooth cables and for our plain cables, we see more like a strain hardening type of situation, and we don't have that. Our post-peak is not that different. After the test, we broke our samples. One of the main observations was that we get lots of radial cracking that starts from one of these phalanges, reaches the cable, and continues to the other phalange, regardless of what torque we put on these nuts, which is like one of the things. And this only happened in the bigger cable. So in super strand cables, which are smaller, this didn't happen. After the test, we broke our samples. We studied the type of the damage we get. We realized that uniformly throughout this whole PhD work, the damage tends to be non-uniform. So towards the exit point or towards the color here on the right, we get lots of damage and a crater and dull edges. As we go towards the bottom section of our sample, we see very sharp edges and very, very little amount of damage. This is, for example, an example of indentation imprint on our grout, which you can actually see. You can see how it shows there. So that means that it's actually something that's useful and it's working. Again, some of the larger scale resin type of the graphs, as you can see, for bolt cables, all of them tend to bundle together around 14 tons. For our plain cables, we see different variations, but our overall load value seems to be the same. For our cyclic testing, so what we mean by cyclic testing in this research is that we did the monotonic testing. We got the peak value of that. We divided by 5, and we made 5 equally spaced loading and unloading cycles. And these are the unloading and loading cycles that we see. And again, our aim was to see what happens over the life of of our structural element when we have changes of stress or environment in the mine or underground space in tunnels. So again, that's the example of our behavior that we can see and how our load pickups happen. For example, here in the 9-strand test, we see that most of them happen in the first 10 millimeters of the test. And again, the details of them are inside our published work. Post-peak investigation for our cyclic test, again, we saw the same thing. We see very sharp edges and very good logs. So we call these logs or like ridges in between them at the end, at the entry point. But towards the color, we see more damage. But obviously, because the resin is more ductile, we are seeing less of a crater. And in the bottom, we see another example of having more damage towards the top. And as we go towards the end, we see less damage. Comparison of the grout and resin in large scale tests, as we can see, is that the difference is very easy to see. So our resin values are much lower compared to our grout values, which are the ones with G. And so it's very easy to see that our resin in this study was much more different, and we didn't have the post-peak behavior that we see the oscillations. So this month, our resin tend to basically have a residual value that was more or less constant. Then we did a smaller scale test. Again, the development of that was that we wanted something to be smaller and faster and cheaper and easier to do. So the initial idea was to use a MTS machine, a multi-testing machine that does compression and testing together. It has a crosshead, and we had the same anti-rotation setup. We had the anchor tube, or the tube that we called it a sleeve, that we wanted to pull the cable out. And on the right, you can see the design we had for our anti-rotation system, which was very similar. We had a welded knob that would slide in this small slot there. We did the test. We realized that, okay, a few issues. the grip of the machine will break the cable, and when the cable breaks, it disintegrates. So we realized we have to put some welds around our cable to make sure that if one of the welds fail, the cable doesn't just end up to be like this. We realized that we need to fill out our cables. Most of them are already filled, but we realized our hollow cables, which were our 9S, 10S, and 12S, we need to fill them out because when they are empty, this grout hole or this breather tool, breather or bleeder tube inside the cable is going to get crushed. So the other thing was change of resin. So we just changed to a different resin. So this resin was called a Geoflex from the same company, Minova. And this one, as you can see, had a different type of failure. It's like a barrel type failure. And it was it's like a strain hardening, it wouldn't even fail. So we even had to go to up to like 2% failure to get our UCS value for it. You can see the difference between the Geoflex and Carbofix, which was the previous resin for the larger scale test. Both of our UCS and our young modulus is much different between them. For sample preparation, as you can see, this was on the left, we see the sample. So this was our anchor tube length. So after the preliminary test, we realized that 300 millimeter anchor tube was too long and it would break the cable. It gets very high to the yield strength of cable. So we went for 150. We had the same anti-rotation weld on it, and we put some extra reinforcing welds on the top. In terms of the location of the bolt, we wanted to have enough utilization of the length of the bolt. So we had the 150 located in a way that we have 100 mils of displacement. So once we pull out the cable in this direction, we actually have the bolt moving through our annulus for at least 100 mil. And on the right, you see the resin injection. Again, this was a two-part resin, which had the air gun, which would get mixed with this straw, and then we inject the grouts with, inject the embedment length that we wanted to pull out the cable from. This was the final test setup. So we had a different machine, much better. We had the anti-rotation section in the bottom. That's this section. You can see the details of it there. And the pull-out. And at the same time, we had, because now we had access to the entry point of the cable, we were able to put the camera and study that. And on the right, you see the broken cables and how they look. The broken samples after the test. For grout and resin, obviously our resin is more ductile, so we see less of a brittle damage, but our grout, you can see the damage, and you see the direction of the pull here. The type of the grout, the type of the graphs that we got from our test are like this. We basically, our post-peak behavior is now, post-peak oscillation was more attenuating, so it just tends to go down. And for our resins, we see type of the strain hardening behavior. Again, the details of them are inside all the papers that we published and the thesis itself. For our cyclic, as we can see, now cycles are much more spread apart compared to larger scale, which was mostly in the beginning of the test. Now we have like much more values, much more displacement, the gap between each of our cycles. The difference between grout and resin for our smaller scale test, as you can see here, is basically our grouts are again superior. We are getting much higher load values compared to our resin values, which are much less and much lower. The difference between our larger scale and smaller scale tests, if we put these two together, we realize that our smaller scale tests, for example, in this Gulayev test, a smaller scale, we are getting our repeatability is less. So we did two tests, but we got everywhere between like 50 kilonewton to 150, compared to the larger scale where the values are bonded together. This 60 and 80 that you see are basically the torque that we put on the external confinement bolts, if you remember from the larger scale section. We see that, for example, in 10S cable, our larger scale test and a smaller scale test tend to match at the 60 Newton meter value of the torque, and in 12S, it basically is similar to the normal test that we did, which was around like 80 Newton meter. This is a little bit confusing because you expect, because our larger scale test had 300 millimeter of embedment, but our smaller scale had 150. So you expect that you get twice the load. But in reality, you see that different cables are behaving differently. Our Gulayev can be around like 50% different, but the other ones tend to be different, and that tennis cable shows that the torque that we put on those bolts have a major effect in them, and our small scale test tends to be more similar to the 60 Newton meter one. The other one, these are the graphs for cyclic for different cables. As you can see, the cycles in the larger scale are mostly in the first 10 millimeter, but in the smaller scale, they are spread apart. And the load values, again, they seem to be, our smaller scales are lower, between around like 50 to sometimes 60, 70% lower, or sometimes, they tend to be much closer. So again, it's very difficult to say that twice the embedment, so we get twice the load because of the change of the confinement and the loading. Post-test observations, as you can see, in the smaller scale test, we get a crater at our exit point. So this is on the top. And on the bottom point, we get a little bit of mismatching between the cables and the lugs that the cables initially was cast into. And we see the damage, again, similar to larger scale, on the right section, which is our exit point, which is our color. Basically, we get a crater and much more damage. And as we go towards the bottom section, we see less damage. This is the same observation for resin. Obviously, resin is more ductile, so we are not seeing that brittle failure, but you see the mismatch of the patterns of the cables compared to the lugs they have on resin. And on the top, we see the damage on the top. And again, in terms of the sharpness of these lugs and ridges, we see that as we go towards the exit point, they become sharper and the damage is less. Numerical modeling, so we wanted to do numerical modeling, so we used the data of our experiments to calibrate a model. We decided to do a 2D model, and 2D, we realized axis symmetry is better. But the problem with that was that cables, you cannot model cables as axis symmetry because they have out-of-plane rotation. So we had to compromise and basically model the cable in 3D and get a cross-section of that and assume that that cross-section is constant during the revolution that happens during axis symmetry. So this is our boundary condition. So we have roller on the top, roller on the sides, and our axis of symmetry have the roller too. And this is our cable, our annulus, and our concrete here. For constitutive modeling for our concrete and for grout, we use concrete damage plasticity, or CDP in Abacus, which is a very famous one. We basically give the parameters for the damage, intention, and compression. And in the bottom section, we see the failure load test of that, the CDP model. For our interaction model, we used a normal mu-s and mu-k, so the static and kinetic friction coefficients. So we assume a very high friction coefficient of mu-s for static. When the debonding happened, we basically lowered that value to a residual value, which was our mu-k. And for calibration of these values, we use our testing that we did during our experiment phase. And this is how we model the cables. So cables, we model them 3D, and then we got the 2D sections of them. These are the outputs we got from our numerical models. As you can see here, for our bolt cables, we got a bit better fits, and it tend to fit with the high values of the oscillations. For our plane cables, we got a good fit for the load, but our displacement was mostly double. And this is the typical values of the stress and damage during the test. So at frame 5, frame 10, and all the way to frame 20, which was the end of the test, we see the development of the radial stress for the bolt cable. This is the left one, and for the plane cable on the right. And in this whole section, we see only the damage output, which is the compression damage and the tension damage. Obviously, our model and numerical model in Abacus is telling us we are developing some tension damage and compression damage in the entry point, but we haven't seen this in the experiment phase. So that means that our numerical model has a little bit of work to do to figure out some of these details. Once we calibrate our model to the best of our ability, we did some sensitivity analysis to see what's the effect of changing different things. So we changed the UCS and module of elasticity, and we realized that, for example, for our bolt cables like 9S, we see that the effect of the change in E of the concrete and grout has a major effect. But for our the UCS of the grout, for something, for example, like the UCS of the grout for something grout and concrete, the grout has little effect, which is interesting because you don't expect that. But for our concrete has a high value, high effect. But the E, the module of elasticity, for actually has a higher effect for our 9-strand cables, which is the bolt cables. But for our super strand cables, we see that the change in UCS of the concrete and grout and the module of elasticity has higher effect on both of them. The other three sensitivity analysis was on the diameter of the cables, on the diameters of the bolt cables, plain cable, and the change in diameter of the bolt. As we can see, the change in the diameter has major effect. However, the most interesting thing is the change of the bolt. So even a 2 millimeter change in the bolt to make it smaller and higher can have like significant effect on the load value. So it's very easy to see, like even like a 2 millimeter increase in bolt diameter give us almost twice the load, or in opposite direction. We studied the barrier language. If you remember, we mentioned it in the beginning. So the way we studied that was that we put a dedicated LVDT on top of our cables, which was tied to the cable and resting on the barrel. And we wanted to see the movement of the barrel relative to these wedges during the pull-out test, to basically see how much energy is lost or how much movement is lost. The output that we got was that for different cables, we get between 5 to up to around 9-10 millimeter of movement that happens during the test. Remember that for this 9 millimeter, the cable has already moved 100 millimeter. So around like 10% of the movement, less than 10%, is actually stored in the barrier language. And we realized that for a cyclic testing, our barrier language basically have permanent displacement. So we have instantaneous load pickup. So we don't lose anything once our cable is unloaded and loaded. And one minor thing that was that we realized that our bigger cables compared to our smaller cables have a deflection point behavior, which might be attributed to the type of the barrier language or the design of them, that we get a little bit of deflection. Very minor thing. The other thing was topic of rotation. So this is a very interesting topic. So first we need to differentiate between different types of, when we say rotation, what do we mean? So we can have unscrewing and untwisting. So unscrewing basically means that when you have your cables with the strands inside the grout or resin, when you pull out the cable, because the path of least resistance is for those strands to slide inside their own lug, they unscrew themselves out of the grout. You can imagine when you are pulling a bolt and nut from each other, because again, because of the pattern is very similar, so you get a little bit of rotation. However, untwisting is the tendency of the strands of the cable to straighten themselves, to come out of the wound position in a straight position. And that happens because when you have a vertical load in the axis of cable, you develop some lateral load that pushes against each of the strands, and they want to straighten. So untwisting and unscrewing happen at the same time when we see rotation. Unscrewing happens inside our grout column, and untwisting happens on a section of the cable that's coming out of the grout column or resin column. So what we did is that we studied the geometry of the cables, realized what's the lay angle and lay length, and we realized that after 100 millimeter of movement, how much rotation they should have. And then after each test, we realized that regardless if our tests have rotation constraint or not, what happens is that our samples will rotate. They either rotate during the test, or we constrain the rotation, and at the end of the test, when we release the load, our samples will start to rotate and go back to a certain angle. And this value is the rotation angle that we measured after the test. As you can see, our plain cables tend to be around like 80 to 100 degrees rotation after the test, but our bolt cables tend to be much lower, but with more variability. And it's very interesting because here for SS, IDS, and GUL cable, we are looking at those values, which is very similar to the mean of these values. But for our bolt cables, we should be getting more, between 100 to 168, but we are getting less. This suggests that bolt cables are damaging the grout. So then during the test, some of the rotation is actually getting lost by unscrewing that happens inside the grout column during the test. So in order to measure this better, what we did was that during our small scale test, we put a camera, and in the bottom section, you see the time of the test. and we see the type of the cable that we test on the top. We put a point here. This is these red points that you see here. We follow this point during the time of the test. So in the beginning, this point was here. As you can see, this point is moving. Again, remember, these tests, they have zero rotation. So rotation was not allowed. But as we can see at the entry point, we see that our cable is rotating. This is the last frame of the test. So at the end of the test, our cable, basically this point had, let's say, 180 degrees of rotation, went on the other side. Then when we release the load, so this is the last frame after we release the load, we see that our cable basically went back, all this rotation went back to almost the same location, but not exactly the same location, which is very important. So we had a little bit of rotation stored in the test that actually was done during the test. And we see it for different cables too. So in the bottom section, we see it, for example, for Gulaev cable, that again, we had rotation. So this point started moving and went to there. And when we released the load, it almost went to the correct location, previous location, but again, around like maybe 10, 20 degrees, not there. And for resin, again, we see the same thing, but this is a volt cable. So in these two volt cables, we actually see less rotation during the test at the entry point. And when it finishes, it almost went back to the normal position it went in, which we can basically postulate because of the bolt is damaging scraping the inside of this annulus compared to these plain cables. It makes a way for itself to actually not store the rotation and the cable to basically eventually move back to where it is. But in plain cables, the strands are basically traveling through the path of least resistant. Okay, a couple of take-home notes or like conclusions to talk about. So confining medium has a major effect. We already saw that between the large and small scale tests and for the torques that preload torques that we put on the bolts. The preload of 80 compared to 60 Newton meter had like up to 50% effect on our test. Rotation had overall, little effect, we can say, for our test that we did. Obviously, we need to study it more. Cable modifications such as surface indentation, structure of bolts significantly changed the behavior of the test. Larger diameter cables create radial cracks, if you remember the picture. Our resin samples that we used had lower loads. And for resins, we realized that the diameter of the cable is very important. And we are not getting, in general, good variability for smaller diameter cables compared to the larger ones, regardless of which test we are doing. Cyclic testing had little to no effect. So it's safe to basically say that it has almost no adverse effect on the behavior. Type of the loading did not change the damage type. So the post-test inspection for both cyclic and monotonic testing was almost similar. And one uniform observation was that the damage tends to be more on the exit point, on the collar, on the borehole collar, compared to the end of the cable. For our barrel and wedge, we realized that less than 10% of the movement is stored in barrel and wedge, but those movements are permanent, and we have instantaneous load pickup when we do loading and unloading. And we realized that the larger cable barrel and wedge have a slightly different behavior, but probably this doesn't make that much difference in the bigger picture of the topic that we're talking about. For our small scale test, we realized that it's difficult to get high repeatability compared to the larger scale tests. We realized that the plain cable tests have lower loads but maintain it for longer, sort of a strain hardening compared to the bolt cables. And we realized that bolt cables tend to all have the same behavior and same load values, even though they have different diameters or different geometry. We realized that the damage is very similar to large scale tests, so we get more damage towards the exit point compared to the entry point. And the bolt cables, we realized that they lose some of their capacity in resin cyclic tests, while plain cables were indifferent to the cyclic and non-cyclic testing. For rotation, we realized that zero rotation test is almost impossible. And because cables are not one unit, they are made of multiple strands that are not connected together, they're just bound together, and they all interact differently with the grout and the ridges on the annulus. And I do even believe that this even happens in the field too. So the idea that we need to do like the absolute zero rotation test, which I believe is impossible, throughout in the laboratory, so we can simulate the effect in the field. I don't think that's something that's feasible or something that's going to give us the output that we desire. But we can actually learn from the observations that because cables are in contact with their grout lugs or resin lugs for longer, we can actually use something like surface indentations to actually use these connections. Remember, rock bolts, because they have those fixed ridges on them, when they come out, when you pull them out, they scrape the whole grout annulus or resin and they damage everything. So you basically don't get that much resistance. But for cable, you can actually, even after 100 millimeter of test, as we saw during my presentation, you actually have basically most of your lugs in place. And especially towards the entry point, they are undamaged. So that means that the cable was traveling more or less inside their own section, compared to, again, rock bolt, which basically scrapes everything off. Bulbs basically interrupt the strand movement in the lugs, so they are like big, chunky, unwielding structures that we have there. And we can actually use this to design cable bolts with bulb locations and surface patterns to actually come up with some very interesting ideas. The difference between large and small scale tests is that smaller scale tests have difficulties with repeatability, so they have higher variability, and so does a smaller scale, some smaller cables. And larger scale tests have a stiffer behavior, so you have a steeper load pickup line, and overall behavior, but at the end is the same. For large and smaller scale tests, the presence of the bulb in a smaller scale test basically overshadows everything. So if you have bulb in a small scale test, it basically scrapes everything off. And the most of the cycles in a smaller scale test happen in the first 10 millimeter in larger scale tests, but in smaller scale tests, they are like a space apart. And the decrease of the load from large to a smaller scale test can be anything between 0 to 50%. It's not as simple as saying that half of the embedment, so half of the load. In numerical modelings, we realized that our plane cables, we were able to reach to the plane cables peak values, but at twice the displacement. We didn't have any attenuations in the plane cables, which basically probably that's a shortcoming of our constitutive models, which we cannot dissipate the energy. Our bulb cables, we reached the top peak, post-peak oscillations, but again, we didn't have that much, we couldn't match the oscillations easily. Again, that's probably constitutive model limitations. We realized that elastic modulus and UCS has less effect for bulb cables, and cable size and bulb size are the most important things. Few recommendations quickly. So cable bolts are not just long rock bolts. So I think we should accept this. Instead of putting passive preload torques on the external confinement, maybe we can come up with a system that we either cast our concrete inside big metal pipes, or we put systems that we can monitor and apply different radial stress and radial pressure. So these have been done. So we have examples of this in literature already. Chemical resins are very diverse. What I used during my study is not the overgeneralization, should not be overgeneralized for every single resin out there. So resins are very interesting, so we need to dedicate lots of time to see different resins' behavior. Smaller scale tests are easier, cheaper alternative to larger scale, but we need more tests to be done in a small and large, so we can map them together, so we can have a function to say, okay, if we do this smaller scale test, that's equivalent of that larger scale test, which connects to the next point, that we need a uniformity between the tests that different researchers in different countries do on cables, and the size of the samples and everything, so we can actually easily aggregate the data and compare everything together and have a good data set. Loading conditions, other type of loading conditions can be studied. Something we use monotonic and cyclic here, but we can use instantaneous loading, or like drop tests, or fatigue tests, or push and pull tests. At least we can do them at like a low level and see what's the effect, and if they had major effect, we can actually dedicate more time. We can choose different numerical models. So, for example, something that inherently can dissipate energy or have failure in it other than FEM is better. So either can be a different constitutive model or like a different numerical model. And the topic of rotation is very interesting and very challenging. It's not as simple as rotation good, bad. So we need to study it independently and dedicate some time to it. And the study, eventually everything that we did here was laboratory study. So we need to have field study to corroborate our findings and match them together, and we can actually see what we found in the lab is actually applicable to the industry or not. At the end of the presentation, I wanted to give you more similar topics of my research group back in the university, which mostly revolves around cable bolts and rock bolts. And these are, if you are interested in what I presented just now, you might find all of this interesting too. And I put the name of the authors and the responsible people for these studies. We can search their name, or we can look at the different work that these people done, and you might find something that you find interesting. There has been lots of work in single, double, and angle shear double test. These are some of the pictures some of the work that has been done. You see the double shear test, single shear test, and angle shear test. Some of the other sister project was drop test. So on the left, you see the pull-out test, but in a drop test. So it's like a 500, 600 kilogram weight that drops on top of the samples. And on the right, you see the drop test and instantaneous loading on the double shear test. Here we see some work on fiberglass bolts. So they are very popular these days because they are immune to corrosion, and more importantly, they are cuttable. So you can put them in the ground and you can cut them with your excavator and with your shearer or whatever that you use. So we see some double shear testing with some infill material between the joints for fiberglass bolts. And we see some rock bolts, rock bolt pull-out test that was done in the university with my colleagues. And as you can see, these are some instrumented rock bolts where they put the strain gauges on the rock bolts inside of them and outside of them during the pull-out, and they actually measured what happens and the development of the behavior, the interaction between the rock bolts and the cable, rock bolts and the grout, or eventually the interaction that happens at that area. So all of these are interesting works that I highly implore you guys to go and study them and see them if maybe you find something interesting. And I thank you for the time and the attention. And please reach out to me if you have any questions or anything that you want to talk to me to. My email was in the first slide, one of the first slides. I'm more than happy to help you guys. And all the best.